In the first session, we will be discussing about the CGTTS validation. So I think most of us are familiar by now. From last 1 year, we have been talking about the CBKT program at BIPM. So these courses, these topics are being covered under the CBKT program of the BIPM. Yeah. So the current discussion of this CGGTS TTS files processing submitted by the NMIs is under the course of name time transfer through GNSS pseudo-range measurements. So there is a course in the e-learning platform with the title time transfer through GNSS pseudo-range measurements. So if participants can register, I think most of you are aware of this, and we have a tutorial explaining the GNSS common view and all-in view methods by Dr. Pascal in this course, and we have an interactive format session of this CGGTTS description in an interactive web page, and there is a software tool CGGTTS Data Analyser. We also have the user manual of the software, and there is a small demo recording of the CGTTS Data Analyzer and the source code for the further development of any interested people to further process the CGTTS files. There is a small quiz and the references. Okay, so just to introduce in brief about the common generic GNSS time transfer standard format. This uh, this is a standard data format for the GNSS time transfer methods based on pseudo-range measurements. This is used mostly for the common view and all-in view time transfer methods using pseudo-range measurements. The observation recorded are at every 16 minutes of interval as per the BIPM tracking schedule. And the time transfer receivers automatically generate this format actually, or else we can use R2 CGTTS by the Royal Observatory of Belgium to convert this RANX into the CGTTS format. There are three different versions of this CGGTTS version formats. One is version which has only GPS. Second one is which has GPS and GLONASS, which has GPS, GLONASS, Galileo, Vaidu, and QZSS. Currently, one single frequency and one iono-free combination is recognized as per each GNSS system. So, for example, for the GPS, it is L1C by A, L1P, and L3P, and for the GLONASS, it is L1C by A, L1P, and L3P. Yeah. So on. So the complete description is mentioned in the CGTTS format in the hyperlink, which is mentioned here. The antenna location should be known better than 3 centimeters accuracy to match the 0.1 numeric precision as per the format actually. So the units are mentioned in terms of 0.1 nanoseconds when we talk about the RefSys values or the RefSV values. So then UTCK labs share regularly their CGTTS files to the BAPM for the computation of UTC. So here is the interactive format of the CGTTS format. So just let me just give a brief introduction about this application. So all the applications developed as a part of CBKT of the time and frequency methodology are department at BIPM are hosted by BIPM and under this domain name. So cbkt-time.bipm.org. So people can come here and they can avail this software applications where there is a CGTTS format description, CGGTTS data analyzer, and the clock data checking and BAPM clock format validation. Okay, so just wanted to show you briefly about the CGGTTS data format description, especially for the new beginners in this area of time transfer through GNSS. So just like the file name itself indicates a lot of information that the first character indicates the type of the GNSS constellation, G for GPS, acronym, like it's a shortcut for the GNSS constellations. The second character indicates is it a single frequency, single channel, or a multi-frequency or a single frequency multi-channel observation. Z for a dual frequency observations. So in this way, we can the last 5 digits, of course, indicates the MJD, and after the dot indicates the time of the day of the year. Yeah. So there is a header in the in this format which indicates the position with the receiver, number of channels, and the lab where it is connected, it is located, and the XYZ coordinates of the receiver and the reference frames. And these are the important. This is the important parameter where after the calibration we need to mention these details of the channel of the frequency wise GPS internal delays of the receiver for the each individual constellation and the frequencies. And this is cable delays and the reference delay and the reference connected to the receiver. And the current version here displayed is the version 2.0, which has a 24 data columns of information, starting with the satellite number and MJD and the UTC time, track length, elevation of each satellite, azimuth, and REFSYS values. So the most important point where we need to stress upon is the REFSYS values, which measure the time difference between the reference connected to the receiver and the GNSS system. So it is the always the UTC-K lab minus the GNSS system time. Okay, and the slope of that readings are also recorded in the CGTTS format. So we have further details about the ionospheric and tropospheric modeling, and also measured and their slope values. And the other important parameter is a GNSS observation code, which is required in the observation of the processing of the CGTTS format. Right. So here we can see each session is of 16 minutes duration. So every 16 minutes, it records the uh, measurements as per this format. Yeah. So as we have seen the same thing currently just now. So this is the application where we can do some hands-on on this application, where we can upload some to the CGGTTS files of the receiver, of any two receivers, and then we can process the do the performances evaluation of the common view and all-in view time transfer technique between the two receivers. Okay, so before we go to the hands-on demo of the receivers of the CGTTS files, so I would like to just give some brief introduction about that. That users can upload multiple CGTTS files and investigate the details of the data like MJD, REFSYS frequency, and their gaps or gems in the data. And the interactive plots helps the user in for detailed observations, can perform common view and all in view time transfer between two receivers data. And these are the available filters, like we can filter based on the GNSS code, measurement code, MJD, satellite selection, and all. So I think let me show you the application first. This is again the CBKT hosting page of the applications. Yeah, so this is the application actually where we can upload two receivers, two set of receivers data, the receiver one and receiver two, and this is a sidebar which we can collapse or expand as required. So once we upload the receiver, we can process this. So I think for the current session, I think we can download the data from the e-learning platform. So once we have an account in the uh, BIPM e-learning platform, so here we have a course catalog. So we can filter the courses based on the provider like BIPM, and based on the topic like time and frequency. Then here is the course on time transfer through GNSS pseudo range measurements. Yeah. So here there are different sections as just I have explained you. So here there is also sample CGTTS data set. So the participants can download directly from here. The same thing which we can download this folder, and the sample data is from NPLI and the MTME lab of Thailand. Right. So let me just show you how we can use this application um, and do the analysis of CGTTS. Yeah. So this is the same sample data set. So let me upload one of the NPLI's GPS data. Once we upload, we need to click the submit button. So the application automatically reads the start and end date of the MJD, and there are it automatically filters the GNSS observation codes which are recorded in the files, in all the files. So L2P, L1P, okay, L2C, right, right. So this is an interactive plot where we can expand it to the full screen, full page. Or we can download the image by clicking here, download plot as a PNG. So the plot is downloaded actually. So this plot basically shows the refsys values, weighted refsys values. It's not directly the refsys values along with the MJD, currently recorded MJD in the files. So this plot data information can be downloaded in a CSV format here as download refsys data, and there is a small metric showing the standard deviation of the dispersion in the data. So scroll down and we can upload the second set of receivers data. So let me upload the GPS multi-frequency, then dual frequencies. So here this is the GPS data, sample data of NMI Thailand. So it automatically reads from the header the content of the lab and the reference connected to the receiver and so on from the start and end date. So here we can filter the selected data, uh, the data which we are interested in looking at. So currently 60315 to 318. So this is now only the 3 days of data. So we can see the complete data as well also. Right. So this is L5C and this is L2P and so on. Right. Yeah. So once we uploaded the two sets of data, so here we will be given three options to filter or process the data. Like choose the satellites. Satellite wise, we can filter uh, the data or filter the processing, and we can filter through elevation mask and through outlier. We can set an elevation mask and set an outlier as well. So once we click the plot common view, so when we scroll down here, we can see two plots which are corresponding to the common view shall appear here. So one shows individual satellite wise performance difference, the common time difference between the two locations through individual satellite wise. So here we can see if we double click on that particular satellite, so it shows only the performance of that satellite during this during this MJD which we have selected for. So this information can also be downloaded here by clicking this button. And here we have the option for GPS common view. This is the performance of the GPS common view link between these two receivers which are located in NPLI and NMI Thailand. So here is the performance of the common view, where we can see that the standard deviation is 15.03 nanoseconds. So then here we have an option to do the all in view analysis as well. But we Let me just to show you quickly how to use this available filters here. So currently the default values of filtering are 15 degrees is the elevation mask, like any observation from the satellite which is more than 15 degrees are only considered. So less than 15 are not considered. And if there is any outliers in the data, so they will be filtered out based on the standard deviation of the data of this performance. So the default value is 1.5 times of the sigma. So once we can change it to 100 till maximum 100 times of sigma. So here we can see that once we increase the outlier limit to 100 times, so here we can see that there are outliers which are clearly visible, where it was actually filtered out through the standard filter of 1.5 times of the sigma. So here we can zoom in horizontally or zoom in vertically also on each plot to see in a better way. So here when we see satellite number G30, so it has some outliers of 500, almost like 500 nanoseconds, 529 nanoseconds outliers during a session of this period. So sorry, okay, yeah. So similarly, there is another satellite here, G12. Yeah. So auto scale and then see. So this is G30 and this is G12. So these are the two satellites which are having an so much of offset outliers during the session during for a short period. So hence we see the final performance of the common view link between these two stations has been degraded in these two instances of the measurements actually. So here and here. So here we can try to filter out the satellite G30 and G15, G12 to see how better we can see the performance. So currently the standard deviation is 22.6. Yeah. So I think G30. Okay. So all select all. Okay. Here we have to select the required satellites. This application is developed on Streamlit. Any click on the application will actually make it to rerun the complete application. So this is one of the feature actually, which is by default. Okay. Yeah. So now just for the visibility, so I am excluding G30 and G12 from this total list. So G30, okay, and G12. Let me see. I just removed G30. Okay. Now it is G12. Okay. Right. So here is a processed filtered performance of the common view link. So here we can, in this application, we can filter and process the data based on individual satellite selection as well, actually. So that will help us in better understanding of the time transfer link through these pseudo range measurements. Yeah. In a similar way, we can do the all-in view analysis as well by selecting the plot all-in view option. GPS all-in view link between UTC NPLI and UTC NIM. So here we can see this is all-in view link. So just below every plot, there is an option to download the data in CSV format. Yeah, here. So here we have filters to filter out based on the MJD, right? This is one option where we can filter out. Second option is like we can filter the data based on the GNSS observation codes. When see now I have selected L5C and here it is L2P. So it will automatically perform the common and all in view based on that. So it will tell you you are comparing two receiver clocks with GNSS time using two different code measurements. So it shows a caution message that we are comparing two different GNSS observation codes within that. So must be aware of the outcomes what we are expecting, right? So and we have filters for satellite wise, elevation mask wise, and outlier wise. So this is how we can explore this application. So let me show you a few observations which we can do with this application. So just before in going into that use cases or test cases. So let me just brief you what is weighted refsys, which is being calculated and used in the current application. So the weighted refsys of each receiver, which is estimated as the sum of the weighted refsys values of all satellites available with respect to their elevation angle. So this is the refsys value, and at each epoch, the sine square of the elevation angle of the each satellite has been weighted and normalized among the all visible satellites at that epoch for that receiver. So so this is how the weighted refsys is calculated as per the sine square of the elevation angle. So this is for the second receiver. So weighted refsys value. So the plots which we are seeing here in the first instance when we upload our where was that? Okay. When we upload our data, uh, the first instance, when we upload our data, so here is a weighted refsys plot which we are seeing and which we can download and save the image as well, save the plot as well. So this is a weighted refsys plot which we are seeing. So the common view in the common view method, this is the average of the difference between the refsys values at each epoch. So this is the refsys values. There is no weighted refsys that is used in common view method. So in case of all in view method, at each epoch, there is a difference of the weighted refsys values. Yeah. A simple visual sample example of how we actually measure the weighted refsys values and then perform the common view time transfer. So in the next slide here, you can see this is the GPS receiver 1 data, which is in version 2E format at one epoch. So the time of the epoch is 1 hour 14 minutes. So this is the elevation and refsys values and the GNSS observation codes. So similarly, this is the GPS receiver data for the second receiver. So when we want to compare, perform the common view time transfer, first we need to identify the common satellites between these two locations at the same epoch. So here satellite number 18 and 10 are the common satellites. And then we need to select the frequency, the GNSS observation codes, either it's L1P or L2P or whatever is of interest. So here we selected L1P, right? And then here we see the refsys values. There are only two satellites and they're of L1P. Then these are the refsys values corresponding to them. So the difference of these two corresponding to satellites, the average of them is the common U time difference. And it should be measured in terms of zero point 0.1 nanoseconds. Similarly, this is all in view where we calculate the weighted refsys of receiver 1 and weighted refsys of receiver 2 of all the visible satellites of the selected GNSS observation code, is it L1P or L2C or whatever. And the features, as we have just seen, all of them. Yes. Okay, see, so these are the some of the use and test cases where we can actually uh, have some observations from the CGGTS format. So, like once we upload data, if we see the weighted refsys plot in this format, so we can derive some conclusion that yes, there is a linear drift in the performance of the reference clock connected to the receiver with respect to the GNSS, right? So and this is another test data sample where we can see the linear drift in the opposite direction. And we can also observe jumps and outliers. So if there is any jump due to a calibration, if the new calibration values are being upgraded, or the change in the lab setup, like any reference 1 PPS input cable has been replaced with a new cable, or any other arrangement is done, physical arrangement. So in that situations, we can see the proper jump, which is reflected in the RefSys values in the CGTTS format. So in the outlier, here we can see, of course, the outliers. Just now we have seen. So here we can also clearly see in the CGTTS, what the kind of phase corrections applied on UTCK timescale actually. So here we can see on every day, this is a sample data set actually of some uh, receiver. So here we can see that every day the time, the reference time scale or the clock connected to the receiver is being phase corrected on a daily basis. And we can also get to know the gaps in the data if there is any gap in the data. So here we can use a outlier due to one satellite we have seen just now. We can filter out the data based on the satellite, selected satellite wise. So here we can see common view with different frequencies. So using this application, you can try to perform common view time transfer with a different frequency combinations, GNS observation codes like L1P or L3P. This is iono-free combination. So GNSS common view link L1P of this sample data set. So this is a single frequency, and this is a iono-free combination where ionospheric contributions has been nullified. Uh, so we can see the periodic observations has been gone in the iono-free combination. Common view and all in view with same receiver. So we once we try to perform common view or all in view method using the same reference data, same receiver data, but with a different frequencies, like different observation codes like L1P and L1C of the same receiver. So it shows us the multipath effects of that L1P and L1C. And if we see L1P and L2P, we will be able to see the iono effects actually. So we can use this application and try to we can learn many things if we have sample CGTTS files and uh, this application. So we can actually have a lot of questions which comes up for the beginners especially, that can need to be actually discussed in detail. So here are some of the observations which you can see for this uh, using this application. So like we can monitor the performance of the UTCK. Just now we saw the gems in the GNSS system. So we can do time transfer through GPS and GLONASS and other GNSS, and we can validate, correlate, or relate the performance of GNSS constellation wise and the performance of the UTC K labs connected to the receivers, and the performance of UTCK steering, accuracy of UTCK with respect to other UTCK, outliers, of course, satellite based effect on time link. So we can filter out satellite wise, so we can see which satellite is affecting the performance, and so we can analyze start think that does one satellite is sufficient for time transfer. So we can just deselect all the satellites and just put only one satellite and can check whether it is sufficient and do we have a continuous link or not. Effect of low altitude satellites. So currently the default filter elevation filter is 15 degrees. So we can change that and see how does the satellite elevation or altitude changes. Outliers in the particular satellite data, yes, they can be filtered. If you have only one time transfer receiver, just now we saw that we can see the atmospheric effects using a different GNSS combination of GNSS observation codes, performance of GNSS, multipath observations. Then here, effect of baseline and method of time transfer. So why perform common and all in view between short and long baseline stations to observe the following. So why all in view is more suitable for long baselines, common view or all in view which is more suitable for short baseline. So we can answer these questions once you have this data. So we can directly drag and drop the data and we can clearly visually see which one is good actually. And we can try to answer all these questions. Yeah. Effect of GNSS frequency on time transfer between two receiver stations. High frequency, so on time transfer between two receiver stations. Yeah. Sure. Why the high frequencies has better performance? Like L1C is at 1575 and L5C is 1176. So we can compare the all common and all in view with L1C and check with L5C and we can compare which one is better. So why ionosphere free combination has better performance than single frequency? Of course, we can also validate that receiver calibration offset. So once the two receivers are having an offset, so we can clearly see that uh, in the plots. Yeah, so I have gone through that course maybe quickly. So so please let me know if you have any questions in this uh, analysis. Okay, so this discussion is about validating the BIPM clock dot data format with the BIPM convention. So the aim of this course, which we going to be introduced in the e-learning very soon, is to submit explain the clock data for file format for submission to the BIPM to contribute to the UTC with proper clock steps and their signs. Right. So I will go through the topics in briefly, like how a laboratory can contribute its clock data to UTC and how clocks data are used in UTC computation and the sign convention to represent the clock corrections which are voluntarily applied on a free running clock and why UTCK lab might make corrections, for example, on a free running clock and how to correctly report clock corrections to the BIPM, especially the sign of the magnitude of the correction, and how to verify clock data and corrections using the software tool which has been developed as a part of this CBKT. So the general information is that the following descriptions mainly are oriented with concern for the participation to UTC, but they are also applicable similar rules for the UTC rapid participants as well. So the detailed explanation of UTC and UTC rapid generation from the clocks data is here in the description, the presentation by Gianna. And the software illustrated here is based on the open source Python routines available here. So yeah. So we shall look into the point that how a laboratory can contribute its clock data to UTC. So there are guidelines from the BIPM website clearly indicating the set of administrative and technical requirements of that. So, but here we will look into the technical parts. The first criteria is like the realization of local timescale UTCK, which represents a real-time approximation of UTC. That should be a timescale locally which shall generate a UTCK with the state-of-the-art commercial atomic clocks and should be maintained in close agreement versus UTC. So the normal current guideline is 100 nanoseconds of 1 sigma value with respect to the UTC. The UTCK should be minimum maintain its time offset. And the criteria two is a time transfer link. So there should be calibrated equipment for time transfer, commonly a GNSS time transfer receiver operated as per the BIPM guidelines. And third one is the measurement capabilities to measure the clock performance with respect to UTCK. Like there should be a capability to measure the instantaneous values of the offset, UTCK minus pre-running at every 00 hours of UTC as and submit them to the BIPM. So in case UTCK labs have one or few clocks that have to be corrected by time or frequency step, the corrections should be recorded as well. So the measurement capability of like a zero point 0.1 nanosecond resolution time measurement system is required at least in order to report these clock performances as per the BAPM format. So the criteria for is sharing the data with BAPM as per the BAPM format. So must be required put the measured data in a particular format and must be able to share the data format using a FTP server to the BIPM. Yeah. So these are the four important technical criteria to participate in the UTC competition. So once we see in with detail about the realization of a UTC local time scale and the time transfer link. So here we the point of generation of the UTCK is referred to as the UTCK reference point that is connected to the calibrated GNSS receiver where it measures the UTCK and the GNSS time differences. So UTCK reference point is a source of UTCK, used as a reference for all measurements for the dissemination of time and so on, whatever. That is a point which is defined as the source of the time. So the calibrated receiver is a calibrated GNSS equipment shall have its delay measured as per the BIPM guidelines. The GNSS equipment calibration guided by BIPM are available. The calibration guidelines are available clearly on the web page. So the third important point is like the measurement of clock performance with respect to UTCK. So for example, this is a UTCK point of generation, like from any offset generator or directly from a master clock or so. So then that in that case, so it need to be connected, compared against with other clocks using a TIC, multi-channel TIC or a phase measurement system. So the options we have is a multi-channel time interval counter or a multi-channel phase measurement device or a switching unit followed by a standard two-channel time interval counter. So the measurements of UTCK minus clock 1 in nanoseconds and the format is 9 point at a resolution of 0.1 nanoseconds should be reported to the BIPM. So this is a measurement system setup required to generate the clock data as per the BIPM format. So the sharing the data with the BIPM as per the required standard format. Once we see the clock data file should be in the format which is prescribed in the format. So just let me open and show you that. So in the BAPM page, all the documents are clearly available. So here is the file which shows the clock data file format and its description and sample file showing how to what is the format which should be read. So the important points which we want to highlight is there is no header prescribed in the clock data format. So please don't add any extra text at the top or the bottom of the data format. So, and after the clock data lines, the step format or the correction and clock steps we shall start without any empty lines. So in case labs has their own free running time scale, the measurements of UTCK minus TAK can also be submitted in the clock data file. To participate in the UTC circular T, clock data should be submitted monthly within the 4th of the following month with measurements spaced by 5 days, that is MJD ending with 4 and 9. to participate in the rapid UTC, daily clock file shall be submitted within Monday of the following week. So the important components are the day of measurement, laboratory code, TA code of the lab if it exists, then clock code and UTCK minus TA time difference if TA is there, uh, UTCK minus clock. So here is the format of the actual measurement system, which must be able to measure at a zero point 0.1 nanosecond of resolution, and this broad range that need to be submitted to the BIPM. Right? This is the time step and frequency steps and epoch of the steps. So here is a sample data file of the BIPM as per the BIPM format, where we can see the MJD, the lab code, and clock one code, and it is the offset UTCK minus clock one. And here is clock two code. A unique code is given to each clock contributing to UTC by the BIPM. You can generate your own code from the BIPM web page as well. The set of instructions are clearly mentioned. So this is clock 2 code and it's offset with UTCK minus clock 2. So this is clock 3 and UTCK minus clock 3. So this is clock 4 and this is clock 5. So in each line, only 5 clocks of information should be given. If there are more clocks, then we should put it in the second line. And then if there are more and more, 4, 5, 6, 7 lines are there. So this is a lab which has multiple atomic clocks. So all the recordings are recorded on MJD ending on 4 and in 9. So this file is corresponding to the circularity submission. Yeah. So just wanted to repeat that there are like first set of data is for 4 and then second set of data is for 9. And here we can see maximum 5 clocks shall be represented in a line. And the clock corrections, the voluntary corrections applied on the clock should be reported in this format. But one must be very clear that only voluntary or intentional corrections applied on a free running clock shall be reported. Corrections applied on a UTCK on a daily basis or a weekly basis should not be or on any basis should not be reported actually. So in the computation of UTC, the UTCK is being nullified. So the performance of UTCK doesn't is not considered as given any weightage in the computation of UTC. So only the free running clocks are being contributed in the generation of UTC. So in the file format at the end of the file, so we need to represent this the step formats in this the step corrections applied in this format. So this is the time step. This is MJD, the fractional MJD on exactly where we have we have applied, and this is the clock code and the time steps. And if there are any frequency steps, lab acronym and the lab code. So that should be added at the end of the file, end of the clock data measurements. So sharing the data with the BIPM. So what is the master clock? So here we can see the master clock is the clock that generate UTCK with or without a phase stepper. So in some of the labs, so where there is no micro phase stepper, so the output of the clock is considered as the primary reference output. So in that case, UTCK is the same as the master clock output. So the difference between them is 0. And if there is a microphase stepper with connected to the master clock, so the output of this is UTCK reference point. Okay, so the measured UTCK minus master clock will contain the offset due to the phase stepper, as the output of the phase stepper is being corrected periodically or when required. This free measurement, this is the free clock and this is a corrected steered output. So there is a definitely there will be a corrections which need to be uh, reported if there are any corrections on the master clock. So to understand more how the clocks or clocks data is used in the computation of UTC, uh, to report them in a proper format, and what happens if there is any wrong format is being submitted. So we need to just go through the process in a step very quickly. So we already, all of us are very familiar that this UTC computation starts from the pre-running clocks contribution and which is generated as the EAL with a weighted average of these free-running clocks, and they are steered with respect to the primary frequency standards and corrected for the leap seconds, and the UTC is generated. So in this process of UTC generation, for the computation of EAL, only the free running clocks are used and the measurement of the clock differences are necessary. The clock 1 and clock 2 and so on. Though there is no role of UTC-K in the computation of EAL. So the UTC-K timescale are not weighted in the UTC computation. So any time or frequency steps on UTC-K shall not be reported in the clock data file. The detailed explanation of UTC and its generation is given here for your references. Okay. So now what exactly that is being done at a BIPM? So if we have a voluntarily applied step correction on a free running clock. So for example, on so and so of day, so when there is a 10 nanoseconds correction applied on a clock, free running clock, so BIPM adjusts its previous data so that to have a continuity in the present and the future measurements. So it adjusts the previous data in such a way this 10 nanoseconds so that the performance of the clock, only the free running clock shall be considered or visible for the computation of UTC instead of a voluntary step corrections. The clocks are weighted proportionally to their predictability and stability, which should not be artificially degraded by voluntary steps. So the weightage of the clock in the UTC computation is based on its pure natural predictability and stability. It's not like artificially generated frequency or time steps that are being applied on the clock. So if a clock is voluntarily corrected by the lab, the applied time or frequency step is to be declared to the BIPM in this particular format. The BIPM will compensate for the voluntary step to maintain the continuity of the clock. So the nomenclature that is required and used by the BIPM and request the NMIs or the DA labs to submit their data format is as follows. The BIPM convention says the time step should be reported as a new clock value minus old clock value. For example, if there is any time step correction on a free running clock, so the new value is 20 and the old value is 10. So the time step applied on the free clock is 10 nanoseconds. But normally, as we have seen in all the labs, what we measure is UTC-K minus clock value. So that is where we compare the microphase stepper output with respect to a free running clock. UTC-K minus clock. So normally, most of the new contributors can start and interpret that this is the new UTC-K minus clock value, and that's the old value, and the difference should come out to be the same. But here we can clearly see there is a opposite sign which comes up if we do it in this in this fashion. So if we are looking at UTC-K minus clock, so we need to report the corrections with an opposite sign, right? So that must be that is very important. This is also mentioned in the clock data file format. So just an example. So once we see there is a UTC-K which is smooth and consistent. So there is a free running clock which is having a 2 nanoseconds of drift per each day. So on some day 3 we adjusted the phase to be like from 2 to 4 nanoseconds or so. So from 6 nanoseconds to 10 nanoseconds. So there is a phase correction, phase jump intentionally applied on the clock. So here, if we have to report this phase adjustment, which is done voluntarily, so the new clock value is 10 and the old one is 6. So the time step is applied is 4 nanoseconds. This is what we need to report to the BIPM. But actually, what we measure is the UTC-K minus clock. So once we see the same scenario here with the 2 nanoseconds of drift per day. So here we can see this is the new value and this is the undisturbed pre-value. So here this is a new UTC-K new UTCK minus clock 1 is 0 and the old value is 4. So 0 minus 4 is minus 4 nanoseconds. So the negative steps, so this is not the correct way actually. So to submit the step corrections, correct nomenclature, so we should put an opposite sign. We should report an opposite sign of the correction if we are looking at UTCK minus the free running clock. Right. So what happens if we report a wrong sign in the step corrections which we are reporting? So when we say correctly declared step, so if there is any correctly declared step, so the minus 10 nanoseconds is being adjusted here and considered to be the uh, consider- and adjusted for its free running behavior. So if it is declared in a wrongly, so instead of adjusting plus minus 10 nanoseconds, so it will be adjusted in as plus 10. So in the computation of the clock UTC, we can see the clock. This will be reflected as a double or twice the actual correction which is being applied. So we must be careful with the very sign convention where we are going to report that. So the sign convention, so once we have this correction applied, so we need to report that. So if we are observing UTCK minus clock is increased by 10 nanoseconds, we should report as minus 10 nanoseconds. So this is a simple thumb rule which we can make a note so that it will be clear, because it will be helpful and clear for the computation of the UTC. The lab reports to the BIPM the measure of UTCK minus clock. So declared time step has to be new clock value minus old clock value. It's not new UTCK minus clock. So here is the somewhere 60817 on between these two 5 days of measurement intervals. This correction, voluntary correction of 10 nanoseconds is being applied on a particular clock. So that shall be reported in the same file. It should not be reported in the later file. So the correction should be mentioned for the current month itself. So they should not be from the previous or the old one or the not earlier than that month.
Bharat, there's a question
Yeah.
for you in the chat.
Yes,
Elena,
please.
would you ask your question out loud so Bharat can answer you? I'm not sure if they're going to ask. Do you want me to read it out loud? It's a little bit of a complicated question
Let
about
me
the
see the
formatting.
chat box. There is a
Already has
chat box.
answered, so I think it is on the format that Aurelie is answering.
Okay, Aurelie's answered, yeah.
Okay. Okay. So once we look at the frequency steps, so again it is the same nomenclature which is required to be uh, noted that just a second. Yeah. So in the frequency steps as well, so we need to report the new clock rate minus the old clock rate. So here, once we see the clock is having a 2 nanoseconds of per day drift. So when it is adjusted for 4 nanoseconds of drift, so it's on the day 4. So it started with a different rate, 6 nanoseconds per day. This is the new format. So we need to report the new value 6 nanoseconds per day minus the old value, that is 4 nanoseconds. But this is with respect to an ideal reference, the definition. But what actually we measure at NMIs or the labs is the UTCK, the output with respect comparing the UTCK minus the free running clock. So here we see the new value is a different one, minus 6 nanoseconds per day, and the new and the old one is the minus of minus. So it comes out to be opposite sign. So always once we are monitoring the UTCK minus clock measurements, we need to be careful in reporting the sign, especially with an opposite sign. Okay. So again, what will happen if we report a wrong frequency adjustment? So instead of nullifying the 2 nanoseconds per day, so it will be adding to the frequency drift the of the previous data in a double the twice the drift which is reported actually. So an artificial frequency step 4 nanoseconds per day appears on the clock actually instead of nullifying it to be 0 nanoseconds. So now I mean 0 or whatever the natural behavior. So it will be instead of 2 nanoseconds, it will be like 4 nanoseconds. So the observation here is that when once we have an UTCK minus clock to be of 2 nanoseconds per day, we need to report that value as a minus 2 nanoseconds per day as a frequency step that is applied to the that is applied on a free running clock. So again, the same observations. So if you are observing UTCK minus clock measures, so put an opposite sign of your measured values, or if you have some other reference which you can, with respect to what you can adjust the actual clock, so then you can report an actual sign. So why there might be some situations why this kind of corrections are applied on a free running clock. So when a clock has an offset versus UTC which is too large to be reported, that means if it is this is the maximum allowed offset which is as per the format. So if a clock is more than this value, so then there is need to be adjustment of phase that need to be done for the free running clock by steering by correcting its phase for once. So there is one such kind of situation, and when the clock rate is considered too large, like if it is drifting so much, so usually instead of about 1 nanosecond, so you may be required to steer its frequency to adjust one of the clock to match other clock. So if you have one or two clocks in the time scale and you want to match the phase adjustments of all of them, so there is some such kind of situation, and correcting the clock time or frequency to improve its accuracy. Change in time scale setup. If there is any change in the time scale step setup, like the cables connected from the clock to the phase comparator are changed, or a UTCK is changed, point of definition might be changed. So some changes in the lab setup if they are done. So if you steer UTCK timescale, no steps should be reported in the BIPM clock file. No matter what clock you steer, master clock or another clock, the time or frequency step should be reported always in the recommended sign convention. If you have more than one clock in your lab, the difference between two clocks should always looks like an undisturbed clock once the voluntary steps are compensated as the BIPM does. So when we look at the comparison between the two clocks at your own lab, and you try to adjust that correction which you applied on one of the clock, so then the difference between these two clocks should be like very smooth. So that validation can be done at your end using the application which we will see just now. Right. So in the application which we will see just now is the concept is used as like this. So assuming we have some few multiple clocks in the lab which are being compared with respect to UTCK point of reference using a phase measurement system or so. So now we have this data recorded for 1 month. So once we upload this file in this application, so what will option is we need to select because we don't have any external reference in the UTCK lab. So what we can do is we can compare, intercompare these clocks to see the performance and step corrections applied in a proper format or not. So select a pivot clock, example clock 2 or clock 1. So one of the application automatically selects one of the all the clocks which are having which are free running, and there are no gaps reported for that clock, and there are no steps applied on that clock. So then there is no missing data, or when there is no steps applied on the clock and there are free running. So all such kind of clocks are selected as a pivot clocks, where you can use that as a reference and compare other clocks. So select the clock you want to check for the step correction applied. So for example, here we select like clock 2 is like it's a free running clock. We have applied some corrections on clock 3. So now we can select clock 3 and compare with respect to the other clock 1 or clock 2, and try to adjust the sign in a different and adjust the sign in a proper way. So select the suitable metric and apply the correction to get visually confirmed data validation. So let me show you the application CBKT. So here is the application BIPM clock format. So before that, let me show you a sample data file of the BIPM as per the BIPM format. So here is the sample clock format, uh, how the actual circularity data reported by a lab, like this is the OP Paris Observatory. Uh, so this is how there is one step on one clock of time step reported on this clock. Right. So for the better understanding, a simple understanding, we had generated a one dummy kind of a file where we have applied a 1 microsecond of correction, 1 microsecond of correction on one of the clock here on on a particular day. So we can upload this file and see as a test case what is happening. So this is a single one-page application where we have just option to download, and this is a upload, and this is a sidebar which collapses for. So here we can browse and upload this file. Right. So as I said, so here in the sample data file which we have uploaded, right? So let me zoom in. So this is MJD, this is MJD, this is lab code, and this is the clock code and clock correction. This is clock 1 and this is clock 2. So there are only two clocks, right? So the 4949 MJD 49 ending with 49 is being reported. So there are only two clocks. So one of the clock has been on one of the clock there is a correction applied of 1 microsecond. So that is what reported. So what this application is looking now, considering that is uh, so here as I said, pivot clock. So the pivot clock is selected based on it is having a continuous data without any gaps or jumps applied or reported in the file. So and there is a simple UTC-K here to compare the clock with, that means ideally is all 000 nanoseconds basically. So now this clock which where the corrections are applied can be compared with the free running clock which is in the same laboratory, so to get the situation for the step corrections. So once we select that clock, so if there are any corrections reported for this clock, they will pop up here. So it will show the MJD timestamp or frequency stamp which is recorded for this clock. So here there are two options like time step action and frequency stamp. So So the default option is not applying, and we can apply this correction and see the performance of these two clocks, clock 1 minus this pivot clock minus the clock which is under observation for its validation of the corrections. So at this point we have the options that we will apply or apply it in a reverse direction of the time step. So if there are any frequency steps reported, so that can also be validated here by applying and applying in reverse direction. So here we have options for to plot this clock data. The clock data means that's the difference between these two clocks. One is a free running clock which is acting as a pivot, and the clock which is has been where the corrections are being applied. So this is a plot which we can see that again, this is an interactive plot. So each on each MJD which is reported, so there is a small vertical line added. So this is the clock difference added. So on this particular day, there is a time step correction. Here we can see there is a time step correction reported in this clock data file on this particular day. So here we can see the sample clock data and the corrected clock data. So right now we didn't apply or any correction on this. So it is there normally reporting what it is there. So now we need to validate the correction which we have reported for this particular clock. So we have options for linear residual to see the linear residuals of this clock, the difference between these two clocks, or the quadratic residuals, or the first derivative. Right. So we can, these are the metrics are provided to visually inspect and validate the sign corrections which are reported on a clock for these voluntary gems. So in the time step, so when we say apply, so we can see the time steps corrections are being applied. Yeah. So when we say not apply, so when previously it was the previous steps when it is of 100K of 100K nanoseconds are being applied voluntarily in this dummy file. So what we have to see as per the BIPM nomenclature is the previous data should be adjusted with respect to the current method of observation. So this data, which is currently at a 4,000, should come up to a range of 104K, right? So if the sign correction is reported properly, like it is minus 1000K, 100K or plus 100K, so we can validate that here. So once we click on apply, so we can see that now the previous the data which is before the day of correction, these 2 points are being adjusted to 104K. Like previously it was only 4K, now it's 104K. So these two data points are being adjusted with respect to the current performance of the clock. So in this way, we can actually validate the correction. So what happens if we apply it in a reverse direction? So previously, when we don't apply, the values of the previous data values are at 4,000, like 4K. Now, if we apply it in a reverse direction, so we can see like it is of minus 100K. So now the current values and my previous values are at a offset of like around 200K. So that means when we apply this correction, so now we can see these previous values are adjusted to 104K and it seems to be reasonable, the proper drift. So here the reporting of minus 100K is correct, right? So this is how we can validate. So in the same cases, so if in some of the cases to magnify this correction, we have taken an example of 100K actually. So, but in most of the cases, the corrections are applied in a few nanoseconds or so, or microseconds. So a few nanoseconds mostly. So in that cases, only the clock data is not sufficient to actually to zoom or or if there is multiple clocks are there or multiple months of data we want to validate. So there are other options where we can see and validate, like is it actually visually we can inspect and evaluate ourselves that the linear residuals are being adjusted properly or not, and the quadratic residuals, first derivative. So the first derivative is one of the best example where mostly situations it will help us to resolve this. So when we apply it in a reverse direction, so it will show the current the difference of 200K between the two consecutive points. Instead of nullifying the difference between the first point and the second point is has jumped from 200K. So normally it should be at 0 and 0 if we don't apply. So this is the previous 0 and this is 100K. Yeah. So this is how we can validate. So once we apply this, here we can see the clock data. So here we have 1, 2, 3, 4, 5 days of measurements, like 5 days of measurements. After the second day, the corrections are being applied. So after the second day, the corrections are being applied. So here we can see the first 2 days, the corrected data is 4000, 4K, right? And after that, there is a 100K correction applied, right? This is the scenario. So now when we apply this kind of uh, when we apply this minus 100K correction as per the BIPM, so we should get our previous data adjusted and it should be in alignment with the next steps or the next data points reported. So here we can also see from the data values of the free running clock with respect to a free running clock which is co-located in the lab, that this sign convention is properly applied and reported especially. Yeah. So let me show you one more case of a frequency. So here we see there are two clocks, this and this. So on one of the clock, there is a zero point 0.2 nanoseconds per day of correction is applied. And so for every 5 days, it could be 1 nanosecond of accumulation of the drift. So 1 nanosecond, 2 and 3. So this is reported here that on so and so clock, on so and so MJD, there is an adjustment of zero point 0.2 nanoseconds per day. But the sign convention, is it minus or plus? So that if to validate that, we can use this application. Uh, just let me refresh and then I will just upload this new data files, new file. So here again, we can see there is only one free clock, which is reported in the data. So, right. So here I think I have uploaded the file which has a time step and also a frequency step together. So here we can see in the plot, we can see that there is a time step just now minus 100K what we have seen, and there is also a frequency step applied here of one nanosecond per day. So that should be like to magnify that we have shown it here like to be 1000 nanoseconds per day actually in this sample file. So here we can see once we apply a step correction, so the step values, the values which are before this applied correction need to be adjusted with this. Uh, then with align should be aligned with respect to the values which are after the date of correction. So before correction, it is at 1000 and it should be moved to plus 100K, near to 100K. This is what we have seen. So at this point on this day, there are no frequency steps, so the applying them will not affect the application in any way. So on the next day, on other day, there are frequency adjustments reported, but not the time adjustment. So here, once we apply, click on these two buttons, they will not help in any action. So, but here there is a frequency step reported of 1000 nanoseconds per day. Then we can see that once we apply, if the sign is properly reported or recorded, so then we can see a smooth behavior of the free running clock. So if the sign, if we expect that no, this is the wrong sign, we may have to report a opposite sign. So when we apply this opposite correction, so we can see there is a break in the drift smooth behavior in a different direction. It started moving in a different direction. The previous values are adjusted to be in a different direction instead of to be aligned with respect to the current corrections actually, right? So in this way, we can validate the BIPM clock data file formats which are being reported uh, uh, for circularity or UTC rapid by using this application hosted on the BIPM. So you can upload multiple files, not just one file actually. So you can validate them applying a different correction. So if I use some other lab test files, so here we can see there is one free running clock. There are multiple steps which are applied. So this is more, each file corresponds to one month. So here it is 3 months of files, and each is ending with 4 and 9 and 4 and 9. And so here there is a frequency step applied, and there is a time step applied here. So, and the time step is 600 nanoseconds, and the frequency step is 18.06 nanoseconds per day. So we can see through the data also whether the previous data is being adjusted and is in aligned with the applied correction when we click on this frequency adjustments or time adjustments. So first we can apply here the time, frequency adjustments which are reported here, and then we can see if there are these time adjustments are being done properly, reported properly. So plus 600. So when we say apply, so this is a time step correction here. So it is in, yes, so all the data before this adjustment need to be in a smooth pass on before and after, so that only the natural behavior or drift of the clock shall be considered for the computation, UTC computation. Yeah. So if we apply it in reverse, so all the previous data is applied in a different direction. So no, so it's clearly that this is not, it should not be minus. So it should be, it is already plus. So when we say apply, now we can see a smooth transition before and after the time adjustments. In the same way, if we see the frequency adjustments before and after, so here we can see the smooth transition between before and after. So when we see the applied in a reverse way, so there is a adjustment in the, there is a different slope adjustments here in that. So in most cases, so this direct simple clock data may not be helpful. So we some few options like linear residual, quadratic residuals, or first derivatives are provided, so that we can easily validate the sign conventions which we report to the BIPM. Yeah. So please let me know if any questions on this application.
Are there any questions for Bharath? You can either just unmute yourself and ask, or you could raise your hand. There's one question in the chat. Jim Skinner,
Okay.
would you like to ask your question out loud?
Sure. I'm not sure if you can hear me, but
I can hear you.
so okay, great, thank you. So in the clock data file for, I'm thinking specifically for UTC, not for UTCR. If there's no header information, if we, let's say we add a new clock or if a clock has been removed, is there a message file format that we're supposed to use similar to UTCR reporting now? Or because historically we've added that as a header, as header information?
Yeah. So as per the format, actually, so we have seen so many like there are cases where there are people are adding a few lines as a header that me and my colleagues are on leave, so we are not able to report that, and so people are reporting their ground level situations as a header file as well. So it is written in the header actually. So as per the format, it should not be mentioned any in the header actually. So it should be communicated to the BIPM team through email. This is what my understanding is, maybe. Right. Okay. Yeah.
Great, thank you.
Yeah. Thank you. Yes. Yes.
I do have another quick question. If
Yes, sir. Please.
so, so currently you can report changes in phase, so steps in phase or steps in frequency that we introduce. Is there any future plans for us to be able to report if a change in drift?
Okay. Okay. Maybe maybe Dr. Patrizia maybe can answer this well. Reporting the change in the drift. Okay. Maybe.
Yes, it is not expected at the moment. Do you think it is a case we have to consider? Because usually we see that the equipment allows time on frequency steps. If it is a change in the drift, it means that there is a different frequency step every day. Am I correct or not? I have never seen the application of a drift by an instrument.
Some of the newer masers that we're testing right now have the ability to allow us to make those changes in drift, but we've not come across an instance where we needed to do that for a clock that was reported. But I was just curious if that was a potential in the future.
Yeah, if it is applied like a changing frequency step, for us is a series of frequency step of changing value. If it is really a change in the drift that I have never seen practically applied, yes, we should know, but at the moment I have never seen it. So if you discover how to do that, it's better we keep in touch.